Welcome to the arithmetic zone, and today we're going to learn about L'Hopital's rule. So L'Hopital's rule is a special method that you can use when evaluating limit, specifically when your limit comes out to one of these two indeterminate forms, 0 over 0 or infinity over infinity. Then what you can do is you can take your limit expression and convert it so that the numerator becomes the derivative of the former numerator and the denominator becomes the derivative of the former denominator. So we didn't change anything going from the left limit to the right limit, but we're just taking the derivative of the numerator and denominator. Be careful. Don't be tempted to do a quotient rule. I know you're looking at this expression and you're thinking, oh, I have to do the quotient rule where I have to divide it by the denominator squared. No, you're taking the derivative of the numerator and denominator separately while keeping the fraction sign intact. So, and again, you can only use this if your limit evaluates to 0 over 0 or infinity over infinity. There's several other indeterminate forms here at the bottom, and these are cases where you can't use L'Hopital's rule, and you would have to use a separate rewrite to possibly get it into a form that you can use L'Hopital's rule, or maybe a different strategy. So those forms are infinity minus infinity, which is very common, 0 times infinity, 0 to the 0 power, infinity to the 0th power, and 1 to the infinity power. There's other indeterminate forms, I'm sure, but those are like incredibly rare. Some of these are already very rare anyway. Like 1 to the infinity power is already pretty rare. So today's examples, we're going to go over some simple problems where we're always going to evaluate to either 0 over 0 or infinity over infinity. So we don't have to do any rewrite. We can just take L'Hopital's rule. But I also want to show you for some of these examples different ways that you could have solved the question. So let's look at our first example right here. The limit of x squared minus 4 over x minus 2. The first step when evaluating any limit is to substitute in the value that x approaches into your expression. So it would be 2 squared minus 4 over 2 minus 2. And 2 squared is 4, minus 4 is 0, 2 minus 2 is 0. So this evaluates to 0 over 0, which is an indeterminate form, which means we have to rewrite this. But it also means that we can use L'Hopital's rule because it evaluates to 0 over 0. So I'm going to rewrite my limit expression. And then we're going to take the derivative of the numerator and the derivative of the denominator separately. So the derivative of x squared minus 4 would just be 2x using the power rule and the constant rule, where we just drop the constant, and then the power, we just move the power or multiply the power by the coefficient and decrease that power by 1 to get 2x. Use the same rules here. And derivative of x is just 1, derivative of negative 2 is just 0. So we're left with the limit of 2x over 1 as x approaches 2. This time, we're going to use the substitution method again. So substitute in 2 for x, and then you will get that your final answer is 4. As I said earlier, for some of these questions, there's alternative ways to solve them other than L'Hopital's rule. For this one specifically, I think there's an easier method other than L'Hopital's rule. If you look into the numerator, you can see that you can use the difference of two perfect squares, and you can take x squared minus 4 and turn it into x plus 2 times x minus 2. So I'm going to rewrite the limit right here. And if we were to apply that principle, so x plus 2 times x minus 2, keep the denominator the same, we can cancel out the x minus 2, and we're left with the limit as x approaches 2 for x plus 2, and then we can simply substitute in 2 plus 2, and then get 4. So we get the same answer with a little less work. So sometimes there are methods that you can use other than L'Hopital's rule, but L'Hopital's rule is so convenient because it's almost like this universal way to solve any limit that goes to 0 over 0 or infinity over infinity. Because, you know, factoring isn't the only option that's available. It's not the only option that may work out for you. Sometimes you have to find a common denominator Other times you may have to use certain trigonometry identities, and for the latter we're going to see that right now. So our second example, we have the limit as x approaches to 0 of sine of 2x all over x. So let's use L'Hopital's rule first. But before we use L'Hopital's rule, or any other method actually, we have to substitute in our x value to see if we can even use L'Hopital's rule. So substitute in 0 for x, so we get sine of 2 times 0, so that's just sine of 0, and this just becomes 0. Sine of 0 is equal to 0 in radians, so 0 over 0, that's an indeterminate form. But it also means that we can use L'Hopital's rule. So rewrite our expression, and taking the derivative of sine of 2x, well, we're going to have to do a chain rule right here. So cosine of 2 of x times the derivative of the inside times 2. Derivative of x is just 1, so this is just 2 cosine 2 of x. So now if we substitute in 0 for x, we get this value, and cosine of 0 is 1, so 2 times 1 is 2, so 2 over 1, and that evaluates to 2. And that's our final answer. Now, if you didn't know about L'Hopital's rule, then there is another way that you could have solved this, but it technically derives from the fact that you can use L'Hopital's rule, but even without understanding it, you might have seen this identity before. But essentially, the limit as x approaches 0, and it must be 0, of sine of any number, so let's just say a times x over x, that will always equal to that special constant value a, and we can see that right here. You can see that right here. The constant here is 2. We use L'Hopital's rule to get the final answer of 2, and this is a special trig identity, but it comes from the fact that you can use L'Hopital's rule. But if you didn't know how to use this, but you knew about this identity, which if you didn't learn about taking derivatives yet or understanding how it works, then you may have seen this before, then you would still be able to solve the question. But it's pretty cool to see where this identity came from. Now we come to our first example where we take the x and approach it to infinity instead of a different constant. So again, our first step is to substitute in what x approaches to. So ln of infinity over infinity. Ln of infinity, even though the graph looks like this, even though it looks like that, ln of x increases without bound. So if we're taking ln of infinity, that would just be infinity. So we have infinity over infinity. And I should probably color this arrow differently because this might be a little confusing. So yeah, this is supposed to be the graph of ln of x. So yeah, we got infinity over infinity, which means that L'Hopital's rule is applicable in this case. So we're going to rewrite our limit expression. Take the derivative of both the numerator and denominator. So the derivative of ln of x is 1 over x, and then the derivative of x is just 1. So we have a little double-decker fraction situation here. We can just rewrite that into the limit as x approaches infinity of 1 over x. And now we can just substitute in infinity. So 1 over infinity, what is that equal to? Well, if you take a number and divide it by an ever increasing number, that number is going to eventually decrease to 0. So the answer for this would be 0. And unlike the previous examples, there isn't really another way you could have solved this question without using L'Hopital's rule. So yes, there are questions where you pretty much have to use L'Hopital's rule in order to solve the limit, and this is one of them. Here's our next example. We have e to the x power minus 1 over x cubed as x approaches 0. So again, our first step is to always substitute in our value that x approaches to. So e to the 0th power minus 1 over 0 cubed. E to the 0th power is just 1, and 0 cubed is just 0. So we have 1 minus 1 over 0 you can see that we do get 0 over 0, which means that we have to use L'Hopital's rule. So we can rewrite our expression. Make sure you always rewrite the lim and what x approaches to if your expression still has x's. Once you substitute in your values, that's when you can drop the lim notation. So we're going to take the derivative of this expression. The derivative of e to the x power is still e to the x power. And because the derivative of x is just 1, it would technically be e to the x power times 1, but we can just say e to the x power. And then derivative of minus 1, just 0. Now the derivative of x cubed, that would be 3x squared. If we were to multiply the power by the coefficient, 3 times 1 is 3, and then decrease that power by 1. So now we have the limit as x approaches 0 of e to the x power over 3x squared. So again, we're going to substitute in our values. So e to the 0th power over 3 times 0 squared. Well, the denominator is going to be 0, and the numerator is going to be 1. And you might be looking at this expression and think, is that another indeterminate form? The answer is no. When you have a number other than 0 over 0, that just simply means that the limit does not exist. So DNE. And that would be our final answer. Now, having a limit evaluate to infinity or negative infinity is also the same as DNE. But 1 over 0 doesn't necessarily mean infinity or negative infinity, so make sure you make that distinction. Now we have our final example for today's video, and like the first two examples, I believe, this one has another way to solve it, another easier way. But first we're going to show L'Hopital's rule, and first we're going to have to substitute in our values. Now, if I were to substitute in infinity for x, infinity squared minus 7 infinity plus 5 infinity cubed minus 9 infinity. You might be a little confused because, okay, well, I have a positive infinity right here, but then I have a negative infinity. Well, we got to focus on the powers. What's the highest power behavior? Well, this is positive, this is also positive, and that's going to forever increase. So essentially infinity over infinity. So what does that mean? L'Hopital's rule. So limit as x approaches infinity, take the derivative of the numerator and denominator. So this would be 2x minus 7. We drop the 5. And then here, our coefficient is not 1, it's 5. And we're not just bringing the 3 down here, we're multiplying it. So 5 times 3 is 15. And then x squared minus 9. So again, let's substitute in infinity. So 2 infinity minus 7 over 15 infinity squared minus 9. Well, it looks like this evaluates to infinity over infinity again. So we got the same indeterminate form twice. What do? Well, you take L'Hopital's rule again. Sometimes you're going to have to take L'Hopital's rule multiple times, and it can get annoying, especially if you're dealing with e's that just won't go away. But it is something we can do in this case, and it is something we can use to get the answer. So the derivative of 2x minus 7, that would just be 2. Derivative of 15x squared minus 9, 15 times 2 is 30. And then we're just left with 30 times x. Negative 9 drops. And this time we're not going to get infinity at the numerator because that's just one constant value. So 2 over 30 times infinity. Remember what I said about any number other than 0 being divided by this ever increasing number. 2 over 30 times infinity, that would just go to 0. And that's our final answer. So what's the other way we could have solved this? Well, I'm going to do it right here in red. Whenever you take the limit of a rational function like this, a rational function, and whenever the x approaches infinity, specifically when x approaches infinity, then what you can do is you can divide the terms in the numerator and denominator by the highest power in the denominator. So I'm just going to go do that real quick. The highest power in the denominator is x cubed. And then for the denominator, the same ordeal. So 5x cubed minus 9x all over x cubed. Remember, it's the highest power in the denominator, which is x cubed. And if we were to do this, then I'm going to just draw a little arrow down here. Or, wow, that arrow sucks. If we were to rewrite this, now these are all multiple terms being divided by the one same term, so we can separate them and break them apart. So what we can write is x squared over x cubed minus 7x over x cubed plus 5 over x cubed all over 5x cubed over x cubed minus 9x over x cubed. Now I'm going to rewrite this again so you can see what's happening. I might not have enough space though, so I'm going to rewrite it. And this time we're just going to simplify those multiple terms. So x squared over x cubed is just 1 over x. 7x over x cubed is 7 over x squared. 5 over x cubed is the same thing. 5x cubed over x cubed, that just cancels out nicely to 5. 9x over x cubed is 9 over x squared. And you should be realizing here is that all these terms, other than the 5, the x is in the denominator, not in the numerator. So if we're substituting in infinity for x and they're all in the denominator, then all of these terms cancel out to 0. And so we're just left with 0 minus 0 plus 0 all over 5 minus 0. So essentially, it's just 0 over 5, and 0 over 5 is the same thing as 0. So this does look like a lot of work compared to L'Hopital's rule, but really, when you look at this expression and you get more practice using this strategy, you should be able to see that, hey, the denominator has a higher power than the numerator, so that means the limit of this expression should just be 0. And you definitely don't have to separate out these terms. I just did that so it's easier to see the logic behind why this strategy works. You could just simply write out the division of all these terms by x cubed and just see that, yeah, this becomes 0 and this just becomes 5, and just skip immediately to this step and then say, oh yeah, the limit's just 0. So that's going to be it for this video. I wanted to show you the power of L'Hopital's rule while also looking at other methods that you could have used to maybe make these problems easier, or maybe if you don't know anything about derivation, just these other methods that would have been helpful. Up next, we're going to do more practice with L'Hopital's rule, but we're going to go over harder examples. These examples, it's not so clear cut because the indeterminate form is not 0 over 0 or infinity over infinity, which means we're going to have to rewrite them in a different way so that we might use L'Hopital's rule or we might just use a different strategy. So, see you guys next time.